Well, today our first speaker is Dr. Sana Vidar. She is assistant professor at the University of Education, and she had been PhD student. She completed her PhD under my supervision. Wonderful time she had with me, and we had done very good work on multiple atoms in optical lattices, which are which is a very basic system in developing multiple atom-based quantum computers. So our work was very much appreciated internationally, and she became the student of the year at Physical Society, American Physical Society, and she got a fully funded scholarship to visit their conference for few weeks, and that was a nice thing. At present she is doing good work on quantum algorithm, and she's the specialist of quantum Grover algorithm. So today she is going to present that work. So I invite her here. Thank you.
Thank you for the kind introduction. Well, today topic which we are going to see is like the Grover's algorithm, which is basically a quantum search algorithm. So I have basically like combined the two sessions, that is the Grover's algorithm and its application and extension. So here is a brief outline of my presentation. First of all, I'm going to give the motivation. What was the motivation behind developing Grover's algorithm? Then I would like to give an overview of what is Grover's algorithm. Then what are the quantum computing foundations which are being used to develop the Grover's algorithm? And then we will like deep dive into and see how it works. And after that, I will like to give the implementation of it in Qiskit for the 2-qubit search, 3-qubit search, and multi-solution search. And after that, doing all and understanding how Grover's algorithm works, we're going to see its future applications and extensions. And in the end, I would like to conclude my presentation, but there is also a catch that I would like to explain the quantum learning path for the students who are like want to develop their skills around quantum computing. So if you want to know about that, stay connected with and till the last. So starting with the first section, that is the motivation. Like why do we need quantum algorithms? So the answer is classical inefficiency. Why classical algorithm become inefficient? Like you can see over here that as the problem size increases, then the runtime grows linearly, exponentially, and you can see over here that the classical approach become impractical. That for the large set of data size or any problem with big structure or size, the computational time is going to increase. But there is always a limitation to that computation. So in order to overcome that, we have certain limitation of classical. After that, we can't like solve the things classically. So we need quantum computing or quantum algorithms in order to like speed up the specific task. But you have to keep in mind that those tasks would be specific. We're not going to like completely like discard the classical system. For the small scale solutions, we will still use the classical computer, but for the large scale problem or those problems which can't be done by the classical computers will be done by quantum computers. So as you guys have already taken the sessions of like the basics of superposition, superdense coding, and teleportation. So you guys have built like foundation, but you just know the things which are like the basics of quantum. And if you want to use them, we need an algorithm. So basically, algorithms are developed, whether they are classical or quantum, to do a specific task efficiently. So what are the basic quantum principles which make it different from the classical? So first of all, there is superposition. You guys have already seen our session with Dr. Hamad, and he has given a brief overview of all of these things very well. So I hope you guys get it. So basically, what superposition is, it is like the classical system exists in two qubits, like either it's 0 or 1. But when it comes to quantum mechanically, it will be in superposition. Like there is 0, 1, and there is like a superposition 0 plus 1. That is, it is going to be in a superposition of 0 and 1 simultaneously. So that's basically a superposition. Next is interference. So how come we are going to use the interference? Like we are going to amplify the right signals or right decisions or right answers or correct answer which we need, and the wrong ones are going to be have a destructive interference. There are signals coming, and the right ones will be amplified, and the wrong one will be like a destructive interference. They're going to be 0. So we're going to get a right amplification of the correct answer. Third one is entanglement. In entanglement, two qubits are linked. So we establish an entanglement between two qubits, and if one qubit is over here and second is somewhere else, like maybe in far away or in space, if we do something over here, then that will be affect the qubit over there, like so far away. So the entanglement or this phenomena is very powerful, and like it only exists in quantum. No, there's no classical version of all of these phenomena, neither superposition, nor the interference, nor the entanglement. The fourth one is measurement. So in case of measurement, when we do the classical computing, we're going to get one result. But when we're going to do the quantum computing, there's a superposition. And when we measure the state, it's going to get collapsed. You will get either of the two states. Let's suppose if we are taking the two qubit states, you're going to get one answer at the end. That is the measurement, the superposition collapse, and we're going to get a classical answer because we need the classical solution or outcome which we can read or which is necessary for our computation and which we want to compute. Okay. So next question is, how are we going to judge whether a classical algorithm is efficient or a quantum algorithm is efficient? So for that matter, there is a big O notation, like we can see over here, which is basically a classical comparison of the running time of classical and quantum algorithm. So that takes very different approaches. Like there is a classical algorithm and there is a quantum algorithm. So how can you say that is a classical algorithm worth it or a quantum algorithm worth it? So there is a big connotation by which we measure which algorithm is more efficient and more fast. So like in the picture you can see over here, the big connotation for the constant, which is like over here, is the best one. The smaller it is, the more efficient it is. And when we're going to increase that is less efficient. So in case of like linear searching, like if we're going to search one by one the thing, so it's like the classical one is like if we have a large data and we need to search one thing inside it, we will search one by one. So it's basically an n step process. So the big notation will be O of n. But for the quantum case, for the Grover's algorithm, which is today's topic, we say that we have a quantum algorithm which is more efficient and it gives us far better computation and fast computation as compared to the classical one. So for the case of Grover's algorithm, we have under square root of n. That is, it's going to quadratic speed up the same formulation which we were earlier doing with the classical one. Now we can do it with the quantum more efficiently. Now here you are also seeing that there are some n factorial bases. Now these are like the classical factorization problem. Factorization can be of everything, but the prime number factorization is really, really difficult. Like if we have a very big number and we need to factorize it, then it will be like really hard for you to factorize it, because most of the cryptic notations, yeah, cryptic things we do in financing or anything, those are basically done with that prime factor factorization. The encryption is saved inside that prime factor factorization. So for that, there is also an other algorithm, which is a very well-known algorithm, which is the Schwarz algorithm, which you will learn tomorrow. Dr. Sabi is going to give a lecture on it. And it's like more efficient as compared to the last one, which is for n factorial, and it's going to be an exponential one. So what's the main goal of developing a quantum algorithm? We want to develop such quantum algorithm for which the big O notation is like for the quantum, it's less, and for the classical, we have, which we like right now have in this, should be greater than that. So we want to develop such algorithms which are more efficient as compared to the classical one. Now, coming towards the overview of what Grover's algorithm is. So Grover's algorithm is basically a unstructured or unsorted at searching of unsorted atoms. Like you can see an example of the Rubik's cube. Like when it is not scrambled, it's full structured. And when we are going to scramble it, like in this form, you can see that it's like an unstructured. You can't see that it's whole yellow here, whole red here. This is like a mixture of everything. So if if we are going to like find something or find one particular qubit or like we're going to find one particular state inside it, it will be really hard. But this is like a very basic example just to teach you that for the case of unstructured data, structured data is when it's completely like having same colors on the either side, and for the unstructured case, it's going to be either scrambled. That is, it's unsorted data. Yeah, means you doesn't have a sorted data, so that you can like find your desired state or desired thing or desired answer inside it. So as you can see over here in the figure, there's a person who is like having lots of books. These are like lots of phone books, and he want to search one number inside this. So classically, it would be really hard for him to open every book, or if he's like manually computing or doing some classical computation, he has to do and go one by one, checking every page, checking everything. If he's lucky, he can find it in the midway or in the start or in between. And if he's unlucky, he might find it at the end. And it will take a long time for him to like search inside it. So in the classical world, the unsorted atom of n database, what the linear search shows that we have to search one by one. We have to look each thing one by one. And on average, if we are like very lucky, we're going to get it beforehand. So minimum number of queries would be n half. Like might be we're going to get the correct answer mid in between, or we get the worst case situation will be that the answer which we are searching for would be at the last. But the quantum world says that for the same unstructured data, if we use quantum superposition, superposition means like the same maze example, like I don't know whether it's explained to you guys or not, but for the quantum search, there is a superposition. Means quantum is like going to start from one state and like it's going to go either way or every side at the same time, because it has the phenomena of superposition. So it can go to any direction at the same time. Because if we're going to start all the states in superposition, then we can search them together. But so for that matter, if we're doing a parallel searching, then the queries are going to have under root n number of times will be taken. So for the classical case, it will take a lot of time, but for the quantum mechanical case, we're claiming that using the Grover's search algorithm, which I'm going to explain ahead, will take less time to compute the same. So example can be that if we have a billion atoms and we want to search them classically, we will at least need 500 millions queries. But for the sake of Grover's algorithm, which is a quantum algorithm, we say we will find it around under square root of n times. So here is an example of, we are taking a 2-qubit example. Like we have 2 qubits, that is 0, 0 states, 0, 1, 1, 0, and 1, 1. If we do the linear search for 0, 1 state, we will have, like shown in the picture, you can see we have 4 boxes. We don't know what's lying inside the box. We have to search the state 0, 1. We will open each box and we'll see whether 0, 1 is the state over there or not. So when we reach the target qubit, we will get it. But it is a linear search that like we have to open each and every box to search whether it is there or not. So this is the classical searching, and for the unsorted data, which is not sorted, it would be very hard for you to find out where exactly is the answer which you are looking for. So the quantum approach would be just leave all the stuff that's written on it, just focus on the bar histograms. We start all the qubits, like we have 4 qubits, we have 2 qubits, and the number of states are 4 because we have 2 to the power n. So when we have 2 qubits, so it means 2 to the power 2 means 4 states. Like we have 0, 0 state, as you can see over here, 0, 1 state, 1, 0 state, and 1, 1 state. So we are having 4 states. What we are going to do is that we start with a superposition, means equal probability of all the 4 states. So you can see over here that we have the equal probability of all the 4 states at the same time. Classically, we were opening each box and checking, but quantum mechanically, we are having a superposition of all the 4 states in the start. So the next step is that we are going to invert the phase of the state which we desired. So like in this case, we want to have a 0, 1 state. So for the case of 0, 1 state, we will flip the sign of 0, 1 state, like inversion, phase inversion of the desired state. We have 4 states, 0, 0, 0, 1, 1, 0, 1, 1. We will invert the phase of the desired state. Inversion means like you have to apply a Z gate or control Z gate on the state to invert it. After that, if we do the average will be like there are 3 positive states and 1 negative state, which is the desired one. But the probability overall is still the same. We have the half probability because in case of quantum mechanics, the amplitudes of the probability are like squared. So for the one we like inverted, we have -1/2, and if we're going to square it, we have still -1 by under root 2. So if we're going to like square it, it's going to be the same. So still, superposition alone can not do the desired stuff for us, which we are looking for. So here, when we again take the average, now we have 3 state positive and 1 state negative. Then the average is going to be over here. Now, if we're going to flip our states around the average, invert our states around the average, the positive states are going to go down, but this negative state over here, which is flipped, when it's going to flip and inverted, it's going to gain that much amount of average which we are like inverting. So in this case, we have the maximum probability of it being there. And if we're going to repeat the same step of like inverting or averaging again and again around this, we're going to get our desired state. If To this point, someone doesn't get the point, they can ask the question. Okay. Like we start with four states superposition, we flip the desired state. Then after that, we did again do the average and invert the state around the average. Like, you can see in the second picture, there are three states positive, one state negative. If you are going to take the average of all of these, now three are positive, not four. So the average is like where the line is shown. If I am going to invert my state around the average, means like these are going to have down amplitude on the opposite side. But this one state, which is a required state, that is the 0, 1 state, when it's already negative, when it's going to be flipped or inverted, it's going to gain that average. So because of that, it's going to gain the amplitude. Then if we repeat this again, then we're going to amplify that state, and which is our correct state. And in this way, we're going to get our correct state. So that's basically the process of amplitude amplification. That with the help of amplitude amplification, we're going to amplify our desired state and can get it in a very little time. So, but there is a limitation of inverting and doing this. So there is under root n times, we're going to invert it. After that, if we're going to invert it, it's going to get negative. It won't gain the same amplitude. And the same process is going to repeat like on the opposite side. So we have a limit up till which we are going to apply the inversion. That is the third step, basically. Inverting around the average. If we're going to do more inversion, then it will be like going towards the negative side rather than giving a higher amplitude, because there is a limit after which there is no like higher amplification, because then other states are also going to gain the amplitudes. So if you guys get this slide, that's the main idea behind the Grover's algorithm. If you still didn't get it, you can ask the question, then we will move ahead. Okay, so what exactly is Grover's algorithm? So Grover developed the algorithm in 1996 at Bell's lab. What this algorithm was developed for, that was basically developed for the quantum search algorithm for the unstructured data, not the structured one, unstructured one. So the core idea was that we're going to initialize the states in the ground state, that is 0, 0 states. Then we're going to apply the header market, means keep in mind the same histogram which I've shown before, that it's going to get superposition. Third is oracle. Oracle is like a black box which knows your desired state, your correct answer, and it's going to flip that. Fourth is the diffusion operator, which is like averaging over this and like amplifying the amplitude of the desired state. And the fifth one is like you're going to repeat that process, but it has a limitation that this process can be repeated only for under root n times, not more than that. And after that, you are going to measure the state, and it would be the desired state which you were searching for. So if we compare the classical and quantum search, then we can see that for the case of classical complexity, we have linear search. So big O notation would be dependent on n. But for the quantum mechanical case, we have O notation to be square root of n, which will be lesser time as compared to the classical one. And the limitation in this case would be that the number of time we can repeat is equals to square root of n. Now, if we have 100 items, then classical search says we need 100, like we need to search 100 entries to see where our desired state is. But for quantum mechanical case, we have just the 10 computation needed to find the desired state or the correct answer. So it will speed up the process 10 times. Similar is the case if we increase it bit by bit and the number of items are going to increase, that is if they are 10,000, then for the classical case, 10,000 searches would be needed. For the quantum mechanical case, only 100 searches would be enough. So it's going to speed up the process 100 times. Similarly, if we're going to increase the number of data set, more and more like quantum supremacy is going to be there. Next is quantum computing foundation. Now we will see what things are required for building Grover's algorithm, like the foundation, which earlier lecture during the same conference have been done. So first of all, we need a qubit because it's a quantum algorithm and a superposition. So for the case of classical, we have 0 or 1 bit. But for the quantum mechanical case, we have a superposition of them as well. Like the state can be existed in 0 plus 1 state. Like means you have like 3 opportunities to do the things. So superposition is like a qubit can exist in a combination of 0 and 1 simultaneously. So for creating the superposition, you uses the Hadamard gate, that is the H gate. So if we have 1 qubit, the number of states, that is capital N, would be 2 to the power n. If we have 2 qubits, then the number of states would be 4. Means we are just raising the power of the 2. So if we're going to have 300 qubits, that's almost all the items in this universe can be taken over. Like if we are going to build one day a quantum computer who can work on 300 qubits, almost all the problems in this world would be solved. So the gates required for building the Grover's algorithm are, first of all, the Hadamard gate. So Hadamard gate is basically for superposition, like the one for the histogram, the first one, where all the states were in the same superposition. So when we apply a Hadamard, that is the H gate, onto 0 state, it's going to convert it into 0 plus 1 divided by square root of n. And if we're going to apply it to the 1 state, that would be 0 minus 1. There would be a difference. Okay. Then we're going to get a poly X gate, which is very similar to the NOT gate. Like if we have a 0 state, and we are going to apply the X gate, it's going to flip to 1. And if it's 1, we're going to apply X gate, it's going to be in the 0 state. So then we have a Z gate, which is basically a phase flip gate. Like what we want to do is we want to flip the state of the desired or correct answer. So we need a Z gate. So for the Z gate, if we're going to apply a Z gate onto 0 state, it's going to do nothing. But if we're going to apply that to the 1 state, it's going to give a phase of negative. Like it's going to invert it. Next is Toffoli gate. That is basically CCX gate. That is, you have 2 control qubits and 1 target qubits. And for that case, if both of the states are 1, then it's going to like flip it. So all the quantum gates are basically unitary and they have preserved the probability and they are reversible. Next is the phenomenon of interference. Like we know all of you have like studied the basic physics courses or like the basic science courses. You have seen that there are waves. And if we like going to project waves onto another, there are 2 possibilities. Either we're going to have a constructive interference or a destructive interference. Same is the phenomenon over here, which we are using to amplify our state. So we want the wrong answer to get a destructive interference and the right answer to get a constructive interference. So for the case of the wrong state, the amplitudes will cancel. And for the case of the right state, it's going to get amplified. So it's very much similar to the noise cancelling headphones which you uses. So basically in that there is the same phenomena that the desired noise which you want to listen is getting amplified and all the others are going to be cancelled out. So that's it. Now comes the oracle. There was an oracle which was like we described in the Grover's algorithm. The main idea of the oracle is to just flip the sign of our desired state. So oracle is like a black box, which will are like going to define, and he knows the solution, but he's not like performing anything onto that. He just secretly go whenever the states pass through it. He just flipped the sign of the correct state. So for the case of oracle function, if you are going to donate it with u of omega, if the state is the one we desire, that's the target state, then it's going to put a negative sign that is going to flip the sign for the correct state. And for the one which are not the targeted one, they will pass as it is. No change will be done on them. So here is a brief implementation of that. Then comes the diffusion operator. Keep the same example of the bar graph, which we have seen, histogram graph. For the amplitude amplification, what we are going to do is that we initialize the states in the same superposition. All of the states, like we are targeting the 0, 1 state. So all of the states right now are in equal probability, that finding each of the state is with 0.5 probability. But our desired or the state we want is 0, 1. So what we're going to do, we're going to invert it, and after that we're going to change the phase of it, and after that we're going to invert it around the average. So after diffusion, all the other states are going to be 0 or near to 0, and the desired state would be amplified and equals to 1. Now, up till now, if you have any questions, you can ask. Okay, then we're going to move ahead. That's for the section 3, which is going to be the deep dive into Grover's algorithm and how it works. Same step, we are going to initialize the state. Doing the superposition, oracle is going to invert the sign, amplitude amplification, and in the end, measurement. All the same processes which we are, like I have explained you earlier as well. Now you can see over here, we have like two qubits, like Q0 and Q1. So first step was to create the superposition. So we are going to apply the Hadamard gate. So we're going to apply the Hadamard gate on the both of these. Next step is to flip the sign of correct state. So the oracle is basically doing its magic, and he knows what's the correct state. So he's going to invert the sign of that. Then comes the diffusion operator. This whole circuit is going to like average it out and invert it so that the amplitude of our desired state is going to be the maximum. And in the end, we're going to measure the state, and it will be like our amplified state would be the one we want. Now we're going to like take the chunks of it and see how the physics around that works. You know the cat and ball notations. So we're going to take, so the first step is like keeping in mind that we have the target state as 0, 1. So we start the state with all of them in the ground state because it's like really easy for us to have the quantum states in ground states, because so in case of the ground state, we consider Q0 to be in 0, Q1 to be in 0. So we can write it like this as well or separately as well. Both have the same. Now, first step is we want to create the superposition. How are we going to create the superposition? By applying the Hadamard gate. So we're going to apply the header mark gate onto Q0 and Q1. So it's a zero state. I have already told you, then when we're going to apply the header mark gate on the zero state, we have a 0 plus 1 state. And the second state is also in 0, so it's also be 0 plus 1 state divided by square root of 2. And when both of the square root 2 are going to multiply, we are going to have a half. Now multiply each term by term. This, first with first, first with second, second with first, second with second. We're going to get a 4 states. 2 qubits, 4 states. Now the oracle is going to do the phase inversion. So it's going to put a negative sign around the state which we set as target. We want the 0, 1 state. So we are going to, so the oracle is going to put a negative sign at the 0, 1 state. So when our states are going to pass through the oracle, our desired state is going to get a flip. Then next step is passing through the diffusion operator. Now here you can see we're going to apply the 4 header marks. Now these are all the same states. We're going to apply header mark on each of them. 0, 0, 0, 1, 1, 0, 1, 1. So if we're going to like open them and expand, after the header mark, we're going to get all of these. Now combining it term by term, like simply do the maths of the coefficients. So we're going to get our psi 3 in the form of this. Now Z OR gate is going to flip the state of 0, 0 state. So it will be going to flip the sign. And after that, we are again going to apply the header mark gates. Now we're going to apply header mark on the psi 4 state. And after that, we're going to get a psi 5 state. Now, if you are going to add these amplitudes, that is for 0, 0, 0, 0 state, you can see there is a positive, negative, positive, negative. It's going to be 0, 1 by 4, minus 1 by 4, plus 1 by 4, minus 1 by 4 for the 0, 0 state. Next, if we're going to do it for the 0, 1 state, you can see that for the first one, it's going to be 1 by 4. For the second one, the negative sign from outside is going to be multiplied. It will be 1 by 4 plus 1 by 4. For the third case, it's also going to be plus 1 by 4. And for the fourth case, it's also going to be 1 by 4. So when we combine all these probabilities, it's going to be 4 divided by 4. And the maximum probability will be 1. Similar is the case over here that for other states, we have the 0 amplitude probabilities. Like if simple math, you can do it yourself, you can verify it yourself. So the output state we get at psi 5, that is for the measurement, we're going to get the 0, 1 state. So when we have like less number of qubits, we're going to get the amplified state as 0, 1. Now comes the implementation. I have like few slides of it over here, but I will show you them on Google Colab, and I will share the link so that all of you can open it as well. Just a minute. I've shared the link. If you guys have laptops, you can open it so that I can explain the codes of Gruber algorithm. I've shared that over there. If you want me to share it on Discord, लिंक कैसे शेयर किया जाए? ईमेल के थ्रू तो फिर अब सबको तो नहीं हो सकता शेयर. मैंने लिंक वैसे शेयर कर दिया है
उनके साथ याद नहीं रहा।
डिस्कॉर्ड पे है आप लोग? अच्छा, डिस्कॉर्ड पे कर देते हैं। आपने सेशन एंड कर दिया? अच्छा अच्छा। I've shared the link in the Discord with the same demo kit. So you guys can open from there. And I also want to share another link. Kindly open the first link which I have shared you, then we will go to the second one. Did you guys open that? We can wait for 1 or 2 seconds and after that we can start again. ओपन हो आप लोगों का? बाकी सबको भी हो गया, इसको इशू है तो बता दे। पास नहीं है वो डायरेक्ट स्क्रीन पे। Okay. So now we're going to implement the Grover's algorithm about which we studied right now onto the Qiskit. So there are many ways to use Qiskit. You can do it on Jupyter Notebook. You can do it on VS Code. You can do it on Colab. You can do it on multi other Python as well, because Qiskit is basically a library of Python. So the first step is, I hope it's like, so the first step is we're going to install the Qiskit. So for that, we are going to use the pip install Qiskit command. Then we need the Qiskit air simulator. So Qiskit air simulator, and then we're going to need the matplotlib for the plotting of our desired states. Now I'm going to take the first example of the 2 qubits, 0, 0, 0, 1, 1, 0, 1, 1. So in the start, we have to, like if you know Python, we have to import the libraries in the start. So which we are going to use in the coming week. So in the start, we are like taking from Qiskit, we are importing the quantum circuit because we are building the quantum circuit for the algorithm. So we will need quantum circuit. So we will import from Qiskit, we are going to import the quantum circuit. In this case, if you don't know exactly what you need to import, you can use a static sign. It will import the whole library, but in that case, your programming will be too heavy. So it's better to import the stuff you require, not all the stuff present inside that library. So first of all, we're going to import the circuits from Qiskit. Then from the Qiskit AR simulator for simulating our circuit. Then for the visualization, we're going to take the histogram plot, and for plotting it, we need the Python library, that is the matplotlib library. We start with the 2-qubit state, that is quantum circuit with 2-qubit states and 2 classical registers. So the number of qubit states you are going to take, the same number of classical registers should be taken by you. Then if you're taking 2 qubits, 2 classical registers. If you're taking 3 qubits, 3 classical registers. So the same number would be written over here, because by the end of the day, when you're going to do the measurement, you're going to do it on the classical register. Then the first step is superposition. We're going to apply the Hadamard gate. So we named our circuit QC having 2 qubits, 2 classical registers. The first step is we're going to apply the Hadamard gate. Then we are applying the H gate. The small h is going to denote the Hadamard gate. Hadamard gate on our 0 and on our first qubit and second qubit. Don't mix it with 0, 0, 0, 1. It's just the first qubit and the second qubit, which are being like written over here as 0, 1. Now we have a superposition after that. Next is what our oracle is going to do. Our oracle is going to flip the sign of our desired state. But the problem is that the CZ gate is only going to flip when both states are 1. So for that matter, here the first state is 0 and the other state is 1. So we can't apply CZ gate to flip the state. So what we are going to do is that we are going to apply an X gate onto this 0 state to make it 1. Now we are going to apply 0 gate, X gate onto the 0 state to make it 1. We have now 1, 1 state temporarily. Oh, 0, 0 state, sorry. On the first qubit, that is the Q0 is 0, and the second qubit is Q1. So we are going to flip this Q1 state, because when we're going to apply the 0 CZ gate, control Z gate, it's going to like flip when both the states are 0. Flip the sign. So in this case, we are going to have, we're going to apply the X gate onto our qubit 1, and which will change our desired state 0, 1 to 0, 0. The first qubit is going to remain the same, and we're going to apply the X gate onto the second one. It's going to shift from 1 to 0, but that's just temporary shift. After that, we're going to apply the CZ gate to make our state negative. So we're going to apply the CZ gate on first qubit and second qubit. What will it do? It will be flipping the sign of 0, 0 state to 1, 1 state. After that, again, we are going to apply the X gate. So this X gate and this X gate is basically going to like cancel the effect of each other. So after this, our desired state, that is the 0, 1 state, is going to have a negative sign. After that, we are going to apply in the third step the diffusion operator. The diffusion operator basically consists of all these gates, which I have shown you earlier. First, we are going to apply the Hadamard gate, then the X gate, then the CZ gate, control Z gate, then again the X gate, and again the Hadamard gate. And after that, we're going to perform the measurement. we're going to measure the state. Now we have defined all the three gates, like we have defined the components of the circuit we're going to build. Now we need some simulator to run this circuit. So we have like a quantum simulator, which we can like locally run on our computer, so that before running it on the IBM cloud computing, we are basically checking our codes over here if they are perfectly fine. For the case of the small bits, the simulation over here is totally okay. But for large number of qubits, we usually like firstly perform them on our own computer. When we are like sure about it, then we are going to give it to the IBM cloud. So the simulator which we are going to use is air simulator. The results are that simulator is going to run the quantum circuit QC, which we have developed, and the number shots are 1024. That's by default. You can like take fewer number of shots, but the more you are going to take the shots, the better the results would be. And in the end, like you're going to count the results or count the number of times which you are like the 1 state, 0 state, how many times these are going to appear after like running the simulation. And like then we are going to print the counts, like how many states are going to get either 0, how many times, 1, how many times, 0, how many times, 1, how many times. Then after that, we are going to plot. Obviously, we want to visualize. We want to see what the results are. So for the better visualization, we will plot the histogram so that we can see or view our plot and can see whether we get the desired state or not. So for that, you are going to use the plot histogram command. Here you're going to give the counts which we measured over here, and for like making it a little better, so that if anyone can see that, he can get what you plot. So you can give a title over there, and in the end, we are going to use the plot show command to get the histogram. Now we have 4 states, that is 0, 0, 0, 1, 1, 0, 1, 1. Now we want the histogram to plot all of them with their counts. So we're going to define the states, that these are the 4 states, and then the computing around that would be counting that how much each state is going to show up, and it's going to save it inside the counts full variable, and in the end we are going to print that variable. After that, we are going to use the plotting command, that is the figure size would be this, the bars, their colors, and everything which we usually do when we are plotting to make it more beautiful, more like eye-pleasing. And after that, for our own sake, we want to draw the circuit as well, so we can see whether the circuit we build is the one we desired or not. So here you can see the outcome. Now the output is the 0, 1 state which we required. So the Grover's algorithm circuit is perfectly like executed. Now there are number of counts that how many states are going to like be in the outcome. So the 0, 0 state is almost like equals to 0 times. 0, 1 state which we need is amplified 1, 0 to 4 times. 1, 0 state is also with like 0 probability. 1, 1 state is also going with the 0 probability. So you can see over here that the plot shows that the target state, which was 0, 1, is amplified by using quantum Grover's algorithm. And in a very few number of iterations, that is square root of n, like we can compute the desired state which we want. So here is the circuit, the same circuit which I earlier explained you on my slides. Up till now, if you have any question, you can ask. If you have any confusion in the code, you may ask. Okay. Then we are going to like extend it. Earlier on, we were doing it for 2-qubit state. Now we are going to do it for the 3-qubit state. Now we are going to increase the number of states. So in this case, we are going to have 101 state as our desired state. So same process which we have done earlier. First of all, the first step is we're going to import all the libraries which are required. Second, we're going to define the quantum circuit. Like in this case, we are going to have 3 qubits. So here there will be 3 qubits and 3 classical registers. After that, you're going to take superposition of all the 3 states. So you're going to apply the Hadamard, that is a small H gate, onto the 3 states, that is 0, 1, and 2. After that, oracle, which we are going to use to flip the state of 1, 0, 1. So the oracle will do its magic using these gates and is going to put a negative sign in front of this state. After that, diffusion operator, which is going to average and flip, average and flip. And we're going to repeat this step. For how many times? Under root n times, not more than that. And then we are going to run the whole circuit on the air simulator, which is a quantum simulator. And after that, we are going to like plot it using histogram command, which are very well known for the Python, from the Python. And for our own sake, we are like printing the circuit as well. So we will like use qc.draw command to like print the output circuit to see it. Now here you can see the outcome that for 001 state, for each of the states, the probability are this. You can see on now you can see not in every case you are going to get the amplitudes of all other states to be 0. They will be like less, not exactly 0 sometimes. For very less number of qubits, you can get 0 states. But for other cases, we have like the very much less probability of the other states and maximum probability of the desired state. So you can see over here that the state 101 has the maximum probability. That is the 3178 times. Now you can see the histogram and you can see that we get our desired state, that is the 101 state. Okay, and here is the circuit for 3 qubits. Now we're going to extend that to multi-solutions. Like we can search 2 states at the same time. Like if you want 2 answers, 2 correct answers to be amplified and rest of them to be like have the destructive interference, you can use the multi-solutions Grover's search algorithm. Now the same steps which we have done earlier, you need to import the libraries first, then creating the quantum circuit with having 3 qubits, 3 classical registers. Creating the superposition using the Hadamard gate. Then with the help of the oracle, you're going to flip the sign of your desired state. So in this case, we want to flip the sign of Q2 and we want to find 100 and 101 state together. So first step, import the libraries. Second step, make the quantum circuit qubits. Third step, do the superposition. Fourth step, use the oracle to flip the sign. Fifth step, you're going to use the diffusion operator to invert it around the average. And after that, you're going to repeat the same diffusion operator as many times you require, but with a limitation of square root of n. And after that, you're going to measure the state. And you're going to run this whole circuit on your simulator. Now, the final outcome is that we're going to get two states, that is the 0, 0 state and 1, 1, 0 state together with a higher probability. We plot the same histogram, we plot the same circuit. Now here you can see over here that the desired states 1, 0, 0 and 0, 1, 0, 1 are having the higher amplitudes, as can be seen over here, and all the other states are like almost with 0 probability. So when you are going to increase the number of desired state, like number of correct answers, like for 1, now we have like two correct answers together. The amplitudes of all the other states is going to be lower. And here's the circuit for the multi-qubit. If you have any question till now, you can ask, or otherwise we're going to go back to the slides. If you are new to Colab, it's very simple. Just go to Google, type Google Colab, and you're going to get this interface. Here, you're going to go to the file and can create a new notebook using you can go to the file and can create new notebook. Then you are going to get this desired notebook where you can write your codes and your outputs and can run your any Python coding. Plus you can change the runtime type. So here you can select between GPU, CPU, T4, GPU for large computation like for machine learning, and so GPU T4 is like very useful. And like simply it's like you can see on the screen that there is an option of code and there is an option of text. With the help of text, you can write the text, and with the help of the code, you can type your codes over here. And then there is a play button over here. You can simply play it and you're going to get the output. Okay, now we are going to go back to our slides. Now, I have shown you all the implementation for the 2-qubit search, 3-qubit search, and multi-search solutions. So this is all the same, that if we want to use it on IBM Cloud or like that, we can use the same setup. Here I have just pasted those codes. Now this is the comparison. We have like done the code for 2-qubit, 3-qubit, and multi-solution. For the case of 2 qubits, we get the desired state 100%. That is, we find our desired state, that's the 1, 1 state with 100% probability. But when we're going to increase the qubits and our desired states are like less in number, we're going to find it with a higher amplitude, but still the other states are still going to exist. So we find the probability 101 for the case of 3 qubits to be 97%. But if we're going to do a multi-search, like finding the 2 correct state at the same time, we're going to get the percentage like this. And all the other states are going to have like a very less probability. Now you can run it the same qubits or the same codes on the IBM Cloud or computing as well. But for the for the case of the problems which has very less number of qubits, the AER simulator, which we usually use, which we have used on our computer right now, is enough. But if your problem is like complex, then you can use it on the IBM Cloud. But The problem is that when you are going to use it on the IBIT cloud, there are the real atoms which are going to take those things, and there will be a chance that you are going to have some noise or error in the outcome. Because the main reason that quantum computer is taking so long to build is that the atoms are very tiny particles and they are like very sensitive particles. So keeping them in like a closed space and performing these all tasks is like really hard. There's always a chance of error, environment interaction with them. So for those errors, there are error correcting codes. Like you're going to like compute your circuit, then there is error if you're going to do it on the real quantum computer. Then you use error correcting code in bit by bit to make those errors fixed. And after that, you're going to get your state, but still there's a chance for the error. So what are we going to do now? Now they are making logical qubits. Now what logical qubits are? Means they are making a qubit which has few numbers of bits inside it, qubits inside it, and they have the power that during the computation, they are going to take care of their errors themselves. Like if there is an error in one atom, they are like technically made like that they are like doing their error correction themselves. So such qubits are called logical qubits. But they are very less in number and they have their own limitation. Now the current work is on distributed logic qubits. Like we have the grids, and in those grids we have like the logical qubits. And we are going to perform our computations onto them. But still there are every step has its own pros and cons. So like people are working on it, people are seeing which will be the best solution, because there are many things which are many companies which are currently working on making quantum computer. Like IBM is working with the superconductors. There is a company which is working with silicon, neutral atoms, photonic quantum bits. So many different companies are using different atoms, and then they have their own limitations. They have their own like good things, bad things, and they have to fix it. So it will take time to build a successful and more efficient and more like which a quantum computer which everyone can have. So the challenge is that there's a big challenge that we're going to get errors and we have to fix it. There are limitations. Plus, quantum computing is very expensive. You need a full setup and you need to take care of your atoms, your qubits, applying those things onto them, keeping them in a refrigerator, which is the delusional refrigerator, and stuff like that. Now we have seen what Grover's algorithm is. I will like again revise it with you guys. So first of all, take any number of qubits, let's suppose 2 qubits. What we're going to do, first step, superposition. Second step, phase inversion. Third step, averaging, flip around the average. And in the end, we are going to like repeat the step under root n times, and we're going to get an amplified state. So the applications of Grover's algorithm is in cryptography, optimization, machine learning, amplitude amplification, NISQUERA. Now, the best thing about quantum computing is that it's merging all the fields. Like, it's not explicitly for the quantum people, for the physics people. Biologically, from the biosciences people, they have their amino acid and structures which are very complex and which have limitations. But when they are going to do with quantum computer, they can go beyond the classical one. Similar is for the chemistry people, that they have the molecular structures, but it takes so long to make any medicine, any drug, or anything because we are working like hit and try. That is the linear search. But when we do with quantum, it's going to find the best possible medicine making strategy, and you're going to get your desired um, drug processing, or like the one which can hit and fix the virus very quickly. Fourth application is for the finance people. Like you have seen that for the finance people, there is cryptography, encryption, which is like securely doing our all the banking stuff or any other stuff, which is basically like anything which we want to like keep it safe, secure, no one can break it. Like the passwords you have, you only know them, your system know them. Like there are like your ATM pin numbers and everything. But when we're going to use the quantum search, there will be problems because quantum is going to break the classical one very fast. So we will see the future applications. The first application is data search and combinatorial optimization. So that's basically we're seeing the future extensions of Grover's algorithm. That was for the unstructured large database. So wherever there is a large database, there comes Grover to save you. So, for a very large unstructured data, which we have in machine learning and other stuff, we can use Grover's algorithm to do our desired task efficiently. Second is the set problems. I'm not like a very expert in these things. Okay? I'm just going to give you the overview about them so that you can know what these things, what on which Grover's algorithm can in actual be implemented. So there is a set problem. Like if I'm going to explain it to you in a layman term, it's like you have an equation and you have solution. You need to find the solution which is going to satisfy that equation. That's basically a logical like setup in which we want to find the desired, let's suppose a b equals to x, something like that. There's a big complex equation and which have variables in which you're going to put the values and it's going to give you the desired outcome. So in order to find them, if we're going to use the classical version, we have to put one every number and then we're going to check whether it's going to satisfy that equation or not. But with Grover's algorithm, we have the power that we can like find the solution in under root n times. 2 to the power under n by 2 times. Then there comes the graph problem, like the problems in which minimum vertex covers, that we are going to color the graph for the shortest path. So Grover provides a quadratic speedup in the worst case scenario, which is like linearly, if we're going to do that, it's going to take so long. If you're going to apply the quantum Grover's algorithm, you're going to do it really, really fast. Then comes the logistic and scheduling. There is a traveling salesman's problem. Like you have your like Amazon like riders or other riders which are like going to bring food and deliveries to you. So if they are going to like deliver to many places at the same time, they need a like best possible pathway. So in the minimum number of time, they can like give all their desired targets to the people. So if they are going to do it classically, it would be very difficult and it's taking so long. But if the same problem is done with Grover's, like quantum mechanics algorithm, then it will like find the best possible solution in very less number of times due to superposition, because it's going to like check all the states at the same time and then will show you the best possible one, and you can like use it. Then comes the cryptographic implementation. Now, as I have already said, that whenever the data or whenever anything is transferred, anything like secure communication, you are like basically going to encrypt that. Encrypt that and using a key. If you might have heard of QKD or simple algorithms as well. Like you're going to have Alice Bob example. We're going to take the Alice Bob example. Alice is the sender, Bob is the receiver. Alice wants to send some information to Bob. How come he's going to send in a secure way? He's going to encrypt that using a key. And Bob is going to receive that in encrypted version and then use the key to decode it. But for the classical case, there's always a chance that Eve is going to intercept and can take the information or leak the information. So when the things come to quantum, they are like in a superposition state. So for the case of a superposition state or a quantum state, if Eve is like going to intercept that state, the state is going to collapse. And with the help of no cloning theorem, you can't like rebuild that state in the same way as it was being sent. So if it's going to be intercepted, Bob is like going to know that the information is already breached. So for the case of cryptographic implementation, there is a AES code, which is like 128-bit code. That's like, you can say, for the secure communication, they are using it. Now, if quantum things are developed and you can use them efficiently and like very easily, there are like limitation due to errors right now, but people are working on them. They will be fixed meantime. So the AES code, which is the 128 AES code for secure encryption or cryptographic use, that code would be going to break within 2 to the power 64, like a root n times. We're going to break that and we're going to get all the information. So it's like really alarming situation. So they have already, like NIST has recommended that all the people who are using the AES code 128 should upgrade themselves to 256 AES, which is like more secure as compared to 128. Because if quantum things like going to develop, they are going to break AES 128 like very fast. And when the AES 128 is going to broke, all the encryption that is done inside that is like out. So similarly, there are hash functions, there are birdie attacks, I'm expert of them, but same is the problem over here that if you have those classically, quantum is there to come and break them. So NIST has proposed to use these fiber and dilithium and spinning to use them for key encryption, digital signatures, and everything. You will get to know about these in tomorrow's session with Dr. Sabit. Now comes the machine learning algorithm. So machine learning is basically like, you have a large data set, you need to perform the task, you have to like do the desired stuff. So machine learning, in that we have a KNN theorem. KNN, that is the K nearest neighboring problem. So if it's like that, So it's like we have a graph. We have like, let's suppose we have steric over here and there are circles over here. Like two kinds of things. Like I'm just explaining it as a layman. I'm not expert on it. These are like two kinds of things over here in this data type. And oops, I was explaining the previous slide for the KNN theorem. Sorry. Nearest neighboring. If you're going to bring another atom, like let's suppose it's going to be a box, and we don't know whether it's a star or it's a circle. So the KNN theorem or whatever it is, it says that if you're going to like see the number of atoms nearest it, that's the nearest neighboring of that box, that would be the if there are more stars over there, it will fall into that category. If there are more circles over there, it's going to fall into that category. But there is like a problem that how we are going to like check it, whether it is this one or that one. So classically, it's going to take the time, but again, this is also a data type, and wherever the data type comes, you have like the chance that you can use Grover's algorithm to do that. So for the case of machine learning, we have also the application of quantum Grover's algorithm that is going to efficiently perform the task we want him to do. So wherever you see data, structured, unstructured data, and it's a problem to do anything with that, always use Grover's algorithm. Next comes the extension, that is we're going to extend the Grover's algorithm to the amplitude amplification and quantum walk. Quantum amplitude amplification, we have already seen the amplitude amplification. So like there are different like things which need like quantum amplitude amplification is the same which we have already seen on the first slide of the bar graph. Same case, we have the desired state, flip that, average it around the flip it around the average, and you're going to get the amplitude, highest amplitude around that. So similar is the case for quantum search. We can like use Grover's algorithm for as an extension of quantum search. And then there is quantum phase estimation, and then VQS, variational quantum search. So wherever searching or unstructured or like unprobability, like you don't know exactly what to do, and like it will take time, large time to compute. Classically, always use Grover's to help you out there and build nice things. So the NISQ era, the challenges we have right now to implement the Grover's algorithm is that we have the errors, the gate errors. Second is the decoherence. Decoherence means like you can say it's an impurity or it's an error inside your quantum computer. Like obviously you can't do all the stuff by keeping it like in a in a closed space. So when we were going to do all the stuff, all the things, the environment interaction is going to be there. When there is environmental interaction, there's going to be a chance of decoherence, like errors and other decoherence. Now, the other challenge is that we have limited number of qubits. Like we can build large number of qubits, but the problem is as we're going to increase the qubits, the error rate also increases. So either we have to sort it with error correction codes, or we have to build such logical bits that they are going to like fix the error on their own and then move to the next step without taking those errors. So there is a limitation that is there to be done. Now, there are different error mitigation techniques and strategies with which people are working and trying to build, and the things that are like going to work for them. So the key takeaway is Grover's algorithm provide approval quadratic speedup. Like linearly, it was big O of n, quantum-mechanically, it's big O of square root of n. But it's specifically for the unstructured database. Then comes the power of quantum. What was that which are being used in Grover's algorithm? The superposition and the interference. Like we're going to search all the things together in superposition at the same time. Then Qiskit make it accessible to all. You can run Grover's algorithm on your own computer without being it to be installed or run on the IBM one. IBM has made the AIR simulator for you. You can run almost all the small scale quantum codes on your own computer and check and verify and develop the things. Now the extension can be in many directions, as I already like we have talked about it. There can be approximate the optimization, quantum walk, quantum phase estimation, and stuff like that. People are like really working hard on them. You can see them, you can check on them. But it has other application in machine learning, finance, cryptanalysis, and all. So the practical advantage awaits fault-tolerant quantum computer, but niche experiments are valuable now. So before taking the question answer, there are a few references given over there, but let's dive into the quantum learning path for the student. So there are many people sitting over here or being online right now, which are like very much want to learn quantum computing, but they don't know from where they should start. So I have made this slide explicitly. I have done all these courses and I would highly recommend you guys to go do these courses and learn the quantum computing yourself. So the first course is from the Stanford University. This course was basically made online during the COVID because people were like sitting in homes. They want everyone to like study new stuff. So they made the basic Python coding available online in the form of a course. So you can search code in place on Google. They have a program running right now, but you can like subscribe it. And for the next year, when they are going to like start this again, you can like join this. And it's a very nice Python programming course. It's not like simple. They are going to like let you type code and this. They have a little like you can say I forget the name, but it's like a robot, let's suppose. And like you have to take that through the loops and everything, and you have to make your own code, Python code, to let that robot do that work. And like you are going to build path, and for that, every task, whether it's for loops, while loops, any other thing like whichever the stuff for coding we need, and then they will like teach you everything step by step. They will have the video lectures one day at a time, and then they will give you coding stuff, homework. You're going to like write them, and like they will in the end they are going to give you the certification as well. So for those of you who doesn't know Python, this course is like very nice course. It will take you from the basics, then all the loops, and then plotting, matplotlib plotting. So if you know that and if you learn from that, you're going to do anything with Python, or at least you can read the codes of Python. Second is, if you want to learn about quantum computing, about Qiskit, about SIP. Now there are like many languages developed by different companies to do the quantum computing. The one Qiskit we are using is from IBM. The Google use CIRQ, CIRQ language for doing the quantum computing. There is another one company, Pennyling. It has developed its own computing language or like library in Python to do its stuff. But you can like for the classical case, we have C language, Python, MATLAB, XYZ. Similarly, for the quantum case, you have like Qiskit, SID, Penlane, XYZ. So whichever language you're going to learn, you can do. But the main, which is like very like developing, and for that you can get the code is Qiskit. So Qiskit is highly recommended. So in order to learn the quantum beginning courses, you can join the Qubit by Qubit program. They offer the course, and it's a very good course. I guess they offer it around the summers, and they take it to the around like March. They have 2 semesters on, and it's online. And due to the difference of time, most of the lectures are nighttime, like around 8 to 10. So you can do any of these courses in that time, because in the night time or in the evening time you are mostly free, so you can take the lectures. Or if you can't take the lecture online, their videos are also available. But taking it on spot online, you can ask different questions, different things if you are not getting it any. But these are like very, very good courses. Then comes the Q word. So Q word is like an organization. It has like various different Q cousins, like they have built it for different countries. Like in Pakistan, we do have that, like in online, but they do show up sometimes, but not that much. But you can like do the Q word. There are 3 different courses. First, you have to do the Q bronze courses that will introduce you to the quantum computing linear algebra, which is going, which will tell you a little more about that, the algorithms, the applications. And then there is quantum gold, which is like the way you can run the quantum protocols. Then when you have all these bases, you can get to the advanced courses, which are like going to show you what's currently right now the best thing that's happening, or the latest research, the latest stuff which is going to happen. So for the advanced courses, you can join the Wominium course or the Wiser course. The Wiser course is right now open, and for the students, it's mostly free. So go and subscribe that. It's not always a thing that you can grab all the stuff out of everything, but you can get something. There was a professor of us when I was doing MPhil at NUST, Professor Dr. Sarkar. We used to have a seminar every week. And most of our students were like, why do we go there? They are like talking about the high stuff, and we don't know about that. And we know. One day, like many students were absent from there. He came to the class and he said, why you guys are not taking? We were saying like, no, we don't get it, what they are saying. He says, that's not the problem. The problem is you have to sit over there. You will get something. If you didn't get anything, at least you will know some terminologies. And when you're going to sit with some people, you're going to be like, oh, I know that, I saw it somewhere. And at some point, if you're going to study about that, you can like grasp it pretty fast than the other. So you have to learn things at your own. Nobody is going to like take you with them and like do every step. You have to put your effort. Now everything is available online. You have to just search it, just write it on Google. You're going to get the best courses, best things about anything, not about computing or anything, like whichever domain you are working, you can find it, you can learn it, and you can learn it from the very basics to very advanced. Next is the IBM certification. So IBM, you can like go to IBM website and you can make your account over there. There are a lot of courses over there. They will take you from basic of quantum information and computing course, then step by step there are courses, and there are like coding as well, and everything in Qiskit is available on IBM for free. You just need to have time. Just need to have desire to learn. So, and there is another Qiskit Global Summer School. It's like around August, and like it's of just 2 weeks, but it's like really hard. But you need to like first study those courses, and then you can jump to the Qiskit Global Summer School. And if you are like going to do that and like fully done those tasks which are being assigned to you, you're going to get the IBM Excellence Certificate. And which is very like kind of flexing thing. So you can have it if you are going to put the effort. You're going to get the certifications, which will take you to many places and which will be useful for you. So that's all from my side. Thank you for your attention. And if you have any questions, you're more than welcome to ask. Oh, okay. Mhm. 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 But I would also like to add that Q bronze, Q silver, Q nickel, they are like every country is who offer them like in a circulation. Like someone is going to give, and you can join any one of them. The course is same, it's all already developed and it's already on their site. You can learn from there. They will teach you, they will like give you quizzes, and if you do all the quizzes and have that minimum percentage, you're going to get the certification. By the end of the day, you need some certifications to prove that you know that thing. Because you can claim that you know that thing, but certification is important as a degree you are doing. So there are, I guess, some online questions. Let me check them. I guess also time is a group in Oh, okay. You guys can get anything from GitHub as well. Like earlier on, there was like a problem that if you are having an error in a code, or people like to find it really hard to get a code. But GitHub was developed to keep those code, and but it was not developed exactly for them. There was a person who was like as if like we do thesis and we like make every version of it and again, and we have lots and lots of folders, and by the end of the day it becomes very hard that we are going to find which folder was the first one and the last one and which has which thing and which has this. So for that matter, that person developed the GitHub. So but then he made it public, and like it has lots and lots of things, and people are so kind enough that they share their code over there so that people can take those codes and go ahead of that. So you can use the GitHub repository as per your requirements. Okay, there is a question that how does Oracle knows the correct answer? Maham Siddiqui. So Oracle is like designed by us. The next session is by Dr. Madiha. She's going to let you know how she's going to develop the Oracle for Boolean stuff, and you will learn about that. But Oracle is basically a circuit designed by us. But whenever the state is going to pass through it, he knows what the job is to be done. So it's like a black box for most of the things. So we explain it in the form of black box, but it's usually created by us. Okay. Multi-search diffusion, maybe some other time. I have Ayaz, I have already you can take the screenshot of this last slide and just Google that, and you are going to get all the stuff you required for learning on your own pace. So, okay, that's all from my side. There are no more questions. I would like to wind up my presentation. Thank you to all for listening so patiently for that much long.
Okay. Good afternoon to my online participants. This is Dr. Matiha Khalid, and we're going to start off from where we left yesterday. A quick recap of what we did yesterday was we studied quantum circuits, and we actually tried to solve quantum circuits through two different methods. One was an intuitive method, and the other was the mathematical method. And then we shed some light on superdense coding. And what superdense coding does, it transfers two classical bits using one qubit at the expense of one EBIT. And the purpose of this superdense coding is to have a lightning fast communication in a secure manner. I hope all my online participants might have solved the questions that I've given. Otherwise, the solution of the question have been given on the online portal by Dr. Sara. Okay, so next, today what we're going to do is we're going to study teleportation and then we're going to move forward. Okay, so the method of studying teleportation would be exactly the same. What we're going to do, number one, we're going to study what teleportation does. Then we're going to look into the circuit of teleportation. And then I would like you to solve that circuit with me on the paper, right? So even if you didn't get anything last time, even if you were not interested last time, I would really like to, forcibly write something on the paper so that you can make a sense out of it. Okay? So can anyone tell me what teleportation does? Yes. What is meant by teleportation in movies?
Disappear from one side and appear on the
Disappear from one side and appear at the other side with the blink of an eye, right? So what does it mean when we say quantum teleportation? So it actually teleports a qubit from position A to position B using a classical channel, right? So teleportation means a person, a thing, disappears from one side and appears at the other end, as the image shows, right? So instead of that, we have a qubit that is with Alice, and after teleportation, that qubit appears at Bob and it moves away from Alice. Okay? Now, for the formal definition, teleportation is a protocol that communicates one qubit using two classical bits at the expense of one EBIT? I would like to repeat that. It teleports one qubit using two classical bits at the expense of one EBIT. Okay? So now can you see a similarity, or rather a difference, in superdense coding and teleportation? Anyone can tell me? In superposition, we were using quantum channel to transfer classical bits. In teleportation, we are using classical channel to transfer quantum information. And in both cases, it's being done at the expense of one EBIT at the time. Yes? Okay. So everyone with me so far? So the scenario here is that Alice is unable to physically send a qubit to Bob. So she's only able to send the classical information. So the problem is that Alice and Bob are connected through a classical channel only, but they want to communicate a qubit from Alice to Bob. Now, can we, while communicating the qubit from Alice to Bob, is there a possibility that Alice can keep a copy of that qubit and Bob can also have it? No or yes? Yes? Why? Let's argue. Why? You said yes. If Alice has a qubit and it wants to communicate it to Bob, is there a possibility that Alice can have a copy of that qubit and Bob can also have that?
You can send this like this.
Okay. What does no cloning theorem says? Unknown means that we haven't measured it yet, yes? So one qubit, since it cannot be copied, it will be either with Alice or with Bob. So in teleportation, when the qubit is translated or teleported to Bob, it is no longer with Alice. So this is an important point, okay? And this is again because of no cloning theorem. Okay, Ji. And security is by default inbuilt in this protocol as well, because anyone who has the other end of the EBIT, because EBIT is a combination of two qubits, so anyone who has the other end of EBIT only can decode the system, otherwise it's impossible. Okay, now let's go to the circuit design. Okay, now what happens is that, again, I want to emphasize that this is the Alice portion. The dotted line shows the communication channel, and this is the Bob's portion. So Alice and Bob share an EBIT. This is an entangled pair which is present at a distance. So in an entangled pair, one qubit is with Alice and one is with Bob. And in addition to this, Alice has another qubit psi, ket psi, and Alice wishes to teleport this qubit over a classical channel to Bob. So these double lines are basically classical channels, okay? So using this EBIT and this psi plus will be communicated through a classical channel to Bob, okay? So one thing that I need you to understand, this is a slightly upgraded circuit because yesterday we went up to 2 qubits, right? And this is a 3 qubit circuit. Number one. Number two, we're going to consider this as a combined circuit and then we'll distribute it and we'll work on it, okay? So take a minute, either get the picture of this circuit or draw it on your paper because we want to solve it layer by layer, okay? So it's up to you. Either you draw it or you get a picture of it. Okay, and another thing while you're drawing the circuit, can you write the value of phi plus Bell state? We used it yesterday as well. 0, 0 plus 1, 1 by are going to be. So we're going to start with that. So we have to know that state, okay? Everyone with me? Okay. Now we're going to start with the cryptanalysis. This is the clean circuit, and these are the three layers which we're going to divide. First is the input. Now this is the generalized version of the qubit that I want to communicate. Alpha ket 0 plus beta ket 1. And I have a 5 plus entangled pair. And first layer actually initializes the input. So what is the input state? And then that input state would experience a C0 gate. Then it would experience a Hadamard gate. And then based on the measurements, we'll apply these gates, right? What does that mean? If the measurement result of this detector is 1, only then the X gate will be applied. Otherwise, the X gate won't be applied. Okay? If the measurement result of this detector is 0, then Z won't be applied. So the same principle that we studied yesterday, but this procedure was at the sender side, now it's at the receiver side. Okay? So we're going to work with that. So there are 1, 2, 3 layers, and this is the final layer where we're going to end. Okay? Now, what is the approach? Top to down or bottom up? Bottom up, right? So if we have a bottom up approach, what is the value of ket pi 0? Write it down. Ket pi 0 is ket 5 plus and the value of the ket that is above that. Yes?
जैसे दो ऑपरेटर्स के टेंसर प्रोडक्ट लेते हैं हम कैसे लिखते हैं I tensor H. Just write the tensor product of this input.
Okay. Write it like that. Forget the tensor. So this is 5 plus. We're starting from the bottom up approach. And this is the general qubit that we want to send. So open that 5 plus as ket 0, 0 plus ket 1, 1 by under root 2. And we have this value and then multiply it with 1 by 1. And open this expression up. And I hope you get this expression. Well, they keep an eye on all the students if they need help. That this is ket 0, 0. Yes, exactly. Now then, okay, then alpha ket 0, alpha ket 0, alpha ket 0 plus beta ket 1. Now multiply them in 1 by 1. It will be 0, 0, 0,
Yes.
alpha
Alpha.
by under root 2.
Alpha plus 0, 0, 1 beta
Yes,
plus 1, 1, 0 alpha.
yes.
1, 1, 1 beta.
Whole multiplied by 1 over under root 2.
Yes.
Yes? Write it down and see the answer. I hope everyone's working. I'm sorry, I like forcing people to work. Yes, shall we move to the next step? You're going to define the next step. So what happens in the next step? Everyone having problem with this? Okay, done. Good. The next step is that a C0 gate is applied on Q0 and Q1, where Q0 is the control bit and Q1 the target bit, and nothing happens to Q2. So I'm referring, starting with the bottom up approach. This is Q2, this is Q1, this is Q0. Nothing happens to Q2, right? So this is identity tensored with C0. And in the C0, Q1 is the target bit and Q0 is the control bit. So only the middle bit will toggle if the LSB side is 1. Only the middle value will toggle if the LSB side is 1. Yes, it will be flipped. only the middle value will be flipped, toggled, changed, inversed if the LSB is 1. So if you've written the answer, then I'll show you the answer. Bottom up approach है. Q2 पे कुछ भी नहीं हो रहा, वो देखें नीचे वाली, सबसे नीचे वाली है, ये देखिए, ये नीचे वाली जो क्यूबिट है, इस पे कोई भी ऑपरेशन नहीं हो रहा. So then, yes, identity tensor with C naught, na? So only the middle qubit will toggle if the least significant value is 1. Nahi. Only the middle qubit will toggle if the least significant value is 1. Least significant value कहाँ है? ये least significant. The middle qubit will toggle only if the least significant value is 1.
First one is 1, right?
Last one is 1. Least significant, last one. So, if anyone can match the answer? Yes? You're becoming experts in circuit solution. The middle value will change if the least significant value is 1. Because the least significant value is the control bit. Yes. Nothing would happen here. This would become 1. Write it again. Everyone with me? Done? Shall we move to the next step? Now you people are enjoying. Okay. Now I want you to solve it by yourself. Well, what's the next step? You have the answer, and taking the bottom up approach, it is I tensored with I tensored with H.
Pro tip, please write neatly.
Pro tip, please write neatly. Yes. Yes. Hadamard only on the last value. The first two values will remain same. Separate the last qubit, apply a Hadamard. If it's ket 0, it becomes ket plus. If it's ket 1, it becomes ket minus. Then open ket plus or ket minus. You'll get a huge expression, then simplify it. Adil sir, आपके लिए तो बहुत ही basic theory lecture है. इसके practical bottom up से आता है. Literature में top down होता है, तो वो लेकिन क्योंकि जब वो circuit उधर उनको पढ़ाना होता है और वो results देखते हैं, तो फिर उनको bottom up के लिए भी होता है. Okay, I'm going to look into my online participants. I hope they're working as well. Okay. Has anyone done? Has anyone completed? It's a very big circuit now, so you have to solve it very neatly. Hadamard के साथ बहुत बड़ा हो जाएगा ना? Simplify करें? हाँ, करें. After this exercise, you'll be able to solve teleportation by hand. Good. Shall I show you the answer? I'm going to work on it for a little while more. Okay, no problem. I'm glad you people are working today. Yesterday it was not that.
We will apply header only first, right?
Last, least significant bit, the last one. Yes.
Get a very big number and then show me that.
बेल बेसिस में कैसे? हाँ, लेकिन मुझे शुरू में मैंने किसी और बेल स्टेट पे किया था, फिर मैं इसको एक और बेल स्टेट में ट्रांसफर करूंगी. I know, solve it. बस बेहतरीन, मैं भी solve करके दिखाती हूँ. So this is the answer if someone wants to compare.
Yes, maybe just look at the symbols.
हाँ, I know. I can't work without my students, so they're the one who.
First take the common and then apply it.
हाँ.
पहले apply करें then
वो किस में छोड़ी? Same बात है.
Common and beta वालों का electric common and then एक header one लगाना.
first
You know, the पहली one है वो
हाँ. So when I say least significant bit, it's the last one. It's at the right. Right? Least significant. Least significant. Okay. So everyone has the answer, tell it. Okay, everyone with me? Now. Okay, Vardha. Now we're going to move to the next step. Okay, those who have. Okay. Okay. Now there's a difficult step. So I need you to focus. Okay. So now what we're going to do, we're going to measure. But what we're going to measure is the last two qubits. That means Q1 and Q0, right? Why? Because the measurement, if I name these as Q2, Q1 and Q0, so the measurement is actually here, right? So in the three values, we have to isolate the last two values and we have to isolate the MSB so that we can measure them. Right now, you're working with three bits in a Keck notation, right? So the most significant bit should be isolated at one end and the least significant pair should be isolated at another end so that we can make a bell basis. So what do we do is that we pick 0, 0 and we pick 0, 0 here. So we get alpha ket 0 plus beta ket 1 divided by 2 ket 0, 0. So we need to isolate two qubits at one side and the most significant qubit at the other side so that I can measure them. So I'm going to repeat once again. The problem is that here we have Q2, Q1 and Q0. Q2 being the first qubit, the most significant qubit, and this being the least significant qubit. Now, since the measurement is here, I need to isolate these two qubits at one side and this qubit at the other side because I'm going to measure these two and I'm going to keep this as it is. Is the problem understood? Is the problem understood? Okay, so what is going to happen is that, for example, here you had the answer. So I'm going to pick the values which has same least significant two digits. That is 0, 0 here and 0, 0 here. So what I'm going to write is alpha ket 1 plus beta, alpha ket 0 plus beta ket 1 divided by 2. Alpha ket 0 plus beta ket 1 divided by 2 whole multiplied by ket 0, 0. Why are we doing that? Because we need to isolate the least significant 2 qubits because we need to measure them. After that, I have a difficult question for you.
Everyone is doing this mistake. Whenever you're taking the comment, you're changing the position. उस LSD को MSD बना रहे हैं. उसको उसी position पे रखना.
Because when you change the position, you actually change the wires. So we don't need to change the wires. So have you done that? Now the next question, I'll repeat that question multiple times, but now I need to measure the isolated 2 qubits, keeping alpha ket 0, beta ket 1 at one side. So can you tell me what is the probability of getting 0, 0? How did you figure that out? Sorry? 1 by 2 square. Yes. So we kept the qubit that we want to transfer isolated, and the rest scalar value is the projection, and we take mod squared of the projection, and we get the value of 0.25. Everyone with me? Shall I move to the next slide? Yes? Okay. So now, as I told you, that if we take the magnitude of the whole thing, that would become alpha mod squared plus beta mod squared. And since it's the two probabilities, it should be equal to 1, right? Because the qubits are normalized. Divided by 4, so the probability of having value 0, 0 as the measurement output is 1 by 4. Having the probability of measurement value 0, 1 is 1 by 4. 1, 0, 1 by 4. 1, 1 is 1 by 4. Yes? Here comes the magic. So again, the important thing is that we will get 1, 1, 1, 0, 0, 1 and 0, 0 with equal probabilities. But the thing is that whenever we get the value 1, we add the appropriate gate, otherwise we don't add any gate. Yes? Yes? Let me repeat. So what happened here is that we reached here, and now we know that we're getting answers 0, 0 with 25% chance. We're getting 0, 1 with 25% chance, 1, 0 with 25% chance, and 1, 1 with 25% chance. Yes? Okay. Now, let's assume that we made one measurement and we got the answer 0, 0. Yes? So if we got the answer 0, 0, that means we don't have anything here and we don't have anything here. Yes? So the answer here should be what? Original answer? Okay. So what happens is that we had this value and this had the probability of 1 by 4 because of the half that we got. And this is the value left. And since we're not applying anything on this, this will be, no operation will be applied. And the output that we're going to attain is alpha ket 0 plus beta ket 1. Yes? Now I have a question. 0, 0 had 25% probability. Now, suppose that we get 1, 0 as an output. Suppose that we get 1, 0 as an output. What happens when we get 1, 0 as an output? Okay, when we get 1, 0 as an output, so the qubit that is being translated is this. See your calculations. It was not always this, it was this. Yes? What operation should I apply on this qubit to make it to the original qubit? Not XGate, right? So what happens is that when the measurement is 1, 0, your algorithm said the algorithm is 1, 0, we just have to apply X. And if we will apply X, then what will happen? What will happen? This will flip, X gate will be applied, and we'll get alpha 0 plus beta gate 1. Yes? Now what I want you to do is see your registers and see the possibility when the output is 0, 1. So if the output is 0, 1, what is the remaining qubit that you have in your papers that you isolated? What is the remaining qubit that you have on the paper? It should be alpha 0 minus beta 1. Isn't that so? So 1, 0 means, 0, 1 means which operator? Z operator. So what happens when we apply Z operator and ket 0? Same. What happens when we apply Z on ket 1? We get a negative sign. So that negative sign is nullified by the negative sign that is already there. So after the application of negative sign, what would it become? Alpha ket 0 plus beta ket 1. Okay? Now I have a question for you. I need you to solve it. If the possibility is 1, 1, right? The possibility is 1, 1. So the qubit state that you already have is alpha ket 1 minus beta ket 0. First, apply an X gate intuitively on this qubit. Then apply Z gate intuitively on this qubit and see what happens to the answer. And can someone tell me what happens? I know original state. How? So first we apply X gate. That means it will become alpha ket 0 minus beta ket 1. Then we apply Z. I did something wrong with this. So when the Z gate was applied, what would happen? Ket 0 remains as it is, and there's a negative sign that is involved in ket Z. So what we get is the original state, right? So I wanted a quiz, but I don't think so. So every time we get the same state, and this is the state that we started earlier, right? So what you all did right now is that you teleported alpha ket 0 plus beta ket 1 from one end to the other end using a classical channel that can carry 0, 0, 0, 1, 1, 0 and 1, 1 with equal probability and can teleport the qubit from Alice to Bob. Yes? Now take, yes?
Qubit to replicate.
No, replicate nahi hui. Because if it was replicated, then it means that it was here and it was here as well. So this is destroyed because it's measured here. So Alice does not have anything now because both of the qubits that it had has been measured. So it had been teleported to Bob. Yes? Any other question?
How much information can be teleported?
As much EBITs as you have. So each qubit teleportation requires one EBIT, one entangled pair. So for example, Alice and Bob were on planet Earth and then Alice had 1,000 EBITs shared with Bob, and then Alice went to Mars, then Alice and Bob can teleport 1,000 qubits. Yes? Any other question?
Can we teleport matter by can we?
Well, I'm not a matter expert. Theoretically, this happens, and theoretically, matter. I mean, if we consider a nanoparticle as a particle, then we're actually teleporting a particle. So theoretically, yes. Experimentally, I'm sorry, I'm not equipped enough to answer. Dr. Sarah, if you want to shed some light. He's asking that if we can teleport matter or not. Not right now. हाँ, not to that extent. So nanoparticles, yes, but पूरा इंसान उठा के उधर से उधर नहीं हम कर सकते अभी.
इंसान भी लेके जा सकते हैं उसको particle
What we are-
मतलब divide
What if we are teleporting the data and where we are teleporting it, and that place we have some machine which is converting that data into matter.
Best of luck with that, and congratulations on the Nobel. Yes, definitely it can be done. Okay, so now I need you all to take a minute and then relate whatever Ma'am Mariam yesterday told you. So she gave you a circuit and she gave you the circuit of teleportation. Just open that circuit up. See if I was right teaching, because गलती तो इंसान से होती है ना, क्या पता मैंने गलत circuit पढ़ा दिया हो. ठीक है? Match that and then we're going to move forward. So 2 minutes for that. Either you can take a break or you can match that. After that, again, we have a lot of work. And for that, I would like to request if you have the laptops, then you can open the Code Composer, IBM Composer I showed you yesterday. It would be great. And if not, then it's not a problem. Okay, so 2 minutes and then we'll start again. Okay, shall we move to the next part? That is the last part for my presentation. Okay. Now again, you need to do more work. I won't be doing very less of the work. Okay. So the next and the last part of my presentation is a continuation of Dr. Sara, what she told. So actually what she told is that Grover search gives you this unstructured search and it marks you a value. Yes? And she was discussing different applications in cybersecurity. So can someone tell me what is the application of Grover search in brute forcing symmetric ciphers, if anyone has a brief background of cybersecurity? Okay, can anyone tell me what is brute force? Yes?
We are trying to reach trying to figure out what we further.
Yes. So the thing is that we have a cipher that encrypts something. We have a plain text, a key, and a ciphertext. So plain text is a plain value that everyone understands. Ciphertext is a jumbled value which can be understood only by the person who has the key. Yes? Okay. So brute force means that I have the ciphertext, I have the plain text, but I don't know the key. So what I'll do is that I'll use all the possible keys to encrypt my plain text, and every time I encrypt, I compare my answer with the given ciphertext. Is it the right answer? Is it the right answer? Is it the right answer? And when I get the right answer, then I know that this is the key, right? So I have the plain text, I have the ciphertext, but I don't know the key. So what I'm going to do is that for a given plain text, I will test all the combinations of key till I get the key that gives the ciphertext that matches my given value. Okay? Now, this problem translates to an unstructured search because we don't know what the value is. We have all the values and we need to check it. Yes? Now, given this, ma'am mentioned that we have oracles. Oracle is nothing but a query model. What does query model means? That it is a black box that serves your purpose, serves your search problem, defines your search problem, right? So my search problem is that I need to make an oracle that performs encryption in a very fast manner, right? So what is going to happen? My oracle is the encryption module. So for that encryption module, all the superposed plain key values will be tested and the correct key value will be amplified, right? So whenever I am working with Grover search in the domain of cybersecurity, my first challenge is to convert a classical algorithm that jumbles up my plain text into a quantum circuit, right? That means that if I have an expression ciphertext is equal to plain text XOR key, XOR is a very small operator, right? But if I write it on a paper that ciphertext is equals to plain text XOR key, and I give you and I ask you to make a quantum circuit out of it, you'll say, I can't make a quantum circuit out of it because I do not see any X gate, Y gate, Z gate, C gate. How can I make a quantum circuit? Yes? So, my next, irrespective of the application that you're using, so those who have engineering background, they agree on one thing that anything that is digital in nature can be broken down into AND or XOR and NOT gates, right? Because these are the basic operator that actually runs on your systems, right? So what we're going to learn in the next coming hour is, given you have a Boolean function, Boolean function means that if you have a function that uses only AND or XOR and NOT function, how can you make a quantum circuit out of it? Okay, so this is step 0 for making an oracle, a binary oracle. Then from the binary oracle, you make a phase oracle, and then that phase oracle is connected with Grover search diffuser so that you can get the amplified output. Okay, so unfortunately, we're going to cover, unfortunately, I have less time. So what I'm going to do, I'm going to teach you how to make a quantum circuit of a Boolean expression. You understand the problem? So what we're going to study in the next hour is how we're going to make a quantum circuit from a Boolean equation. Everyone with me? Okay. So again, I told you that if we want to do that, we want to know that how can we make a circuit for AND or NOT and XOR gate, right? So if we know how to make the basic building blocks, then we can do anything. Yes? So let's make the basic functions first. What is the quantum analog to NOT gate? What is the quantum analog to NOT gate? Poly X gate? Yes? So whenever you want to implement an inverse, you simply apply a NOT gate, and in quantum domain, you apply an X gate, right? So write it down on your papers that the quantum analog to NOT gate is an X gate. Quantum analog to NOT gate is X gate. Everyone with me? I'm glad you're writing today. You were not writing yesterday. Okay. Next is the XOR gate. Now, number two, write it down. The quantum analog to XOR gate is C0 gate. I'll show you how, but quantum analog to NOT gate is, to XOR gate is C0 gate. Now, why I'm going to say that? We're discussing the top to bottom approach, okay? So we have the C0 gate. Here we get the target bit as it is, control bit as it is, and the target bit is transformed. Yes? Now, if we see the truth table of this, we can see, if we see the truth table of this, now what is the truth table of XOR function? आसान अल्फाज में same पे 0, different पे 1. Yes? Okay. So let's check the output now. If the control bit is 0 and target bit is 0, what is the output of target bit? 0. If the control bit is 1 and target bit is 1, what is the output of target bit? Target bit ka output 0. So what have we said earlier? Same pe 0. So when the inputs were when the inputs were 0 0, the target bit output was also 0. When the inputs were 1 1, the target bit output was again 0. Yes? With me? Now take a minute and verify कि different पे 1 आता है.
दोनों को लगाए एंड देखा आपका टारगेट बिट कहाँ से क्या है.
I'm sorry, if I had a board, it would have been much easier, but unfortunately I don't have a board, so you have to do it by yourself.
Draw the circuit every circuit draw the input stage below the mask.
Weather is very strict with these things, okay? So you have to do it. So if someone has access to a computer, after that, the next simulation would be on IBM Composer.
A पे सब 1 लिखें, B पे 0 लिखें, कंट्रोल बिट का आउटपुट क्या है?
Target bit का output क्या है?
हाँ, ये 0 है.
So if the control qubit is 1 and target qubit is 0, what would be the output? Control qubit is 1, target qubit is 0, control qubit is 1, target qubit is 0, what would be the target output? If the control qubit is 0, target qubit is 1, what is the target qubit? So different पे क्या आया? Same पे क्या आ रहा था? XOR function हुआ? So when I say that C0 is the analog to XOR function, complete this sentence. I want you to complete this sentence. C0 is analog to XOR gate when the output is measured at the target qubit. When the output is measured at the target qubit. Okay. So now if even then someone does not agree with me, so open your code composers and we apply a C naught gate, initialize to 0, 0, the output is 0. We initialize both to 1, 1, the output is again 0, right? And in the next gate, if the control qubit is 1 and the target qubit is 0, and vice versa, the output would always be 1. Okay? So you can test it on your composers as well. So take a minute, write it down, and the next gate you're going to prove me. With me? Shall we move to the next gate? Okay. I want you to write a sentence first. Quantum analog of AND gate, quantum analog of AND gate is Toffoli gate when output is taken at a target qubit. When output is taken at the target qubit. So quantum analog to AND gate is a Toffoli gate when the output is taken as a target qubit. Okay? इसका ये मतलब है that the inputs A and B are given here. A and B are given at the control qubits. T is initialized to 0. We don't change it. And check the output here. Right? If this is 0 and 0, the output would come out as it is. Yes? Let me repeat. For the Toffoli gate to act as an AND gate, I'm going to keep the target qubit initialized to 0 at all times. I shall keep the target qubit initialized to 0 at all times, and the input is given at the two control qubits. Okay? Now, given the target qubit is initialized to 0, and the input is given on A and B, tell me that if the input is 0, 0, what would be the output on target qubit? Okay? So if the input is 0, 1, and the control qubit is initialized to 0 again, what would be the output? Who said 1? Toffoli gate only flips the target value if both the values are 1. Okay? So if the value is 0, 1 and the target bit is initialized to 0, what would be the output? And can someone tell me the last case? 1, 1, that means that the target qubit should be flipped. So it becomes 1. Yes? So I'll give you a minute. Either you see these circuits or you use your composer to verify what you have said. You have your IBM composers open with you? Try that. If you want to give an input 1, what would you do? X gate. Yes. Okay. With me so far? Shall we move to the next step? Next step is a little bit difficult. You have to take a minute. You have to think about it. And then you have to solve it by yourself. Okay? Now, the quantum analog to OR gate, the quantum analog of OR gate is a combination of X and Toffoli gates when output is taken at the target qubit. And below that, please make this circuit. So this is the circuit for OR gate. These two control values takes the input. The target value is initialized to 0, and the output of this output after this X gate gives you the output of OR between these two inputs. Okay? So draw a circuit on your paper. Draw the circuit on your paper. So we have two inputs. Input A would be fed to this target bit, to this control bit. Input B would be fed to this control bit, control qubit, and the target qubit would be initialized to 0. Okay? And the output would be observed after this X gate. Okay? So the input would be given to the control bits before the X gate and here both before the X gates. Now if you want to solve that and verify that, you know how to solve the circuit. I hope you know how to solve the circuit, right? But for now, draw that circuit and just mark the positions that the input to the OR function, is given before the X gates on the control side. And target qubit is initialized to 0 and the output will be observed here. Okay? Now I have a very important question. Take 5 good minutes and see if I initialize this to 0 and this to 0 and this to 0. What should I get here? Then write 0 here, 1 here, initialize it to 0 and see what the output here we get here. So make a truth table of 0, 0 output, 0, 1 output, 1, 0 output, 1, 1 output. And see this truth table, does it resonate with OR gate or not? You got the problem? You got the problem? Okay. OR gate is a binary function. It takes two values as input and one value as output. Yes? So these are the places where you're going to give the input. These are the two places where you're going to give the input. And this is the place where you're going to check the output. So make a truth table that check all possible values. That means, number 1, put 0, 0 here. Solve the circuit intuitively. Get the answer here and write it. Then input 0, 1. Solve the circuit intuitively. Check the answer. Then 1, 0. Then 1, 1. Check the answer intuitively. And the truth table, check whether it resonates with OR function or not. Now this is the test of your circuit solution. This is your test of how well you were listening to me yesterday. तो देखो ना इसको मजा नहीं आएगा और ये एक्स गेट लगाने आई क्यों लगाने और गेट चेक कर रहे हो कि एंड चेक कर रहे हो और का ये सर्किट है अगर इसके अंदर इनपुट लगानी है तो मुझसे पीछे लगाओगे ये पूरा सर्किट ड्रॉ करो इधर नहीं ना यहाँ पे एक्स लगाओ इधर डिलीट करो उसको एक्स लगाओ फिर भी निकालो आइडेंटिटी डिलीट करो बैरियर लगाओ आइडेंटिटी सारी डिलीट करो ये क्या है इसको ये इनपुट की साइड है, ये आउटपुट की साइड है। अब अगर जीरो जीरो वो आइडेंटिटी मुझे पता है आपके बारे में कैसे करके, बट उसको इस तरह देखो पहले पूरा। अगर आपने जीरो जीरो चेक करना है तो ये जीरो जीरो है, तो आउटपुट पे यहाँ जीरो जीरो है तो आउटपुट जीरो है। अब अभी देख एक गान लगाओ फिर देखो सारे करके। हाँ जी, कैन आई हैव एन अपडेट? No. It is Toffoli gate is a 3-qubit function. So it takes 3 qubits as an input and gives 3 qubits as an output, but we are only measuring the target qubit. We're not using the other 2 qubits. The measurement operator is on the third, that is the target qubit only. So have you done that? Good. You have access to Composer? Okay. So if someone does not, if someone has access to Composer, or if someone can do it like that, it would be great. Otherwise, please use the Composer. If you don't have the Composer, you have circuits here. You can verify the circuits at home. I've made the Composer circuits as well. Okay? Now, do you need time to solve the question or should we move forward? Okay. Okay, Ji. So now, if I have this kind of mathematical expression in which input A is XORed with input B, is XORed with input C, is XORed with input D. Right? So verify, is this circuit correct? So we have XOR functions. XOR function is replaced by which operator? C0 operator. So here what is happening, that Q0 is being XORed with Q3 and we're getting the answer here. Right? This answer is then XORed with Q1 and we're getting the answer here. And this answer is then XORed with Q2 and we're getting the answer here. Right? So the final answer is on this line and we're getting the XOR of these 4 functions. Yes? Okay. Can I make this question slightly difficult now? Yes? I promise this is the second last question. Okay. So now what I want you to do is just replace this XOR with AND function. So this is Q0 and Q1 XOR Q2 XOR Q3 and make the circuit. Everyone with me? Q0 and Q0 and Q1 XOR Q2 XOR Q3. So only the interaction between Q1 and Q2 would change and rest of the circuits would be connected by XOR function. Make the circuit. So by the end of this lecture, you should be comfortable making the circuits and understanding the circuits. That was the whole point. Okay, make the circuit. So what is the quantum analog of AND function? What is the quantum analog to AND function? Toffoli gate. So is this possible to implement the circuit in 4 qubits or do we have to increase the number of qubits? So we'll have to increase number of qubits, right? So to implement the updated circuit, we might need 5 qubits instead of 4. start making it. So please ask me if you have any question. After that, I'll just give you an overview of how phase oracles are made, and then we'll conclude the lecture. So the updated circuit is Q0 and Q1 XOR Q2 XOR Q3. So whatever the answer we get from Q0 and Q1, so first draw Q0 and Q1. So it will be a 3-qubit circuit in which Q0 and Q1 would be given as an input, and the third qubit that we name Q3, so Q2 would be the output. Now that output would be XORed with our next input Q2, and that output would be again XORed with Q3 to get the final answer. Make sense? Can I see the answer? So only one was AND gate and rest of the ones were XOR gate. Yes? अरे हमने सारे AND ही बना दिए. नहीं बोला था. नहीं मैंने कहा था ये दोनों AND है, ये XOR है, ये भी XOR है. आपने ये ठीक बनाए हैं, लेकिन अभी और नहीं ये भी ठीक नहीं बनाए बेटे. बिकॉज देखो आप इधर जो आंसर आ रहा है AND गेट के लिए दिस शुड हैव बीन 0. AND bit क्या था? It is a Toffoli gate with target bit initialized to 0. तो ये AND gate आपने ठीक लगाया है. ये वाला AND gate ठीक इसलिए नहीं चलेगा क्योंकि ये initialized to 0 नहीं है. तो आप क्या करोगे? इसके लिए एक नई qubit बनाओगे और इसको इधर करोगे. इसके लिए एक नई बनाओगे, इसके लिए एक नई बनाओगे. फिर जवाब आएंगे उन दोनों का AND लोगे, उन दोनों का AND लोगे, फिर जवाब आएगा उसका AND लोगे. समझ आया? ओके. So I'll quickly like to wind it. Question है तो पूछ ले. So the next slide I'll give you the steps of making phase oracle and then we'll conclude. And if you have composers, please try that on the composer. Okay, Ji. So with that, this is how we make a phase oracle. So in phase oracle, what happens is, now I need your attention. Varda, we'll do it a little bit later, okay? So now the question was, this was the question. First, we made the binary oracle for that, right? So we translated this equation into a simple circuit. But Grover search requires a phase oracle, right? So what do we do? A very superlative kind of a thing. What we do is, number one, we implemented our function. So this is the function that you recognize. Yes? Q0 XORed with Q3. The answer is XORed with Q1. The answer is XORed with Q2. So this much of the three operators you recognize from the last circuit. Yes? First step is to translate this output to the ancilla bit. Ancilla bit क्या करती है मैं भी आपको बताती हूँ, ठीक है? So whatever the final answer you've got, you just use the C naught gate to shift it down, okay? And then systematically reverse all the operations. So you can see that for the first 4 qubits, this circuit is a mirror image of each other, separated by the C naught gate. Yes? So step 1 is to transfer the output to the auxiliary bit, and the second, apply all the operators in reverse order. Okay? And this is the phase kickback part. So phase kickback, anyone knows what phase kickback is? So in phase kickback, okay, for making phase kickback, you have to give the input of ket minus to the auxiliary bit or to the ancillary bit. Okay? So how do we get ket minus? Ket 1 followed by Hadamard, right? And then of course, while we were replacing all the operators, we have to replace all the operators here as well. Okay? So for the binary oracle, you use the analogs and you make the circuit. For the phase oracle, you transfer the output to the extra bit, which I'm calling the ancillary bit, and you reverse all the operations. An ancillary bit is initialized as ket minus. Okay? Now what phase oracle does is that the positions where the output should have been 1, the output would actually have a 180-degree phase. All the values will have same input, but the values that have a 1 answer will have a 180-degree phase. And this kind of circuit is actually used in Grover search. So this is a valid phase oracle. When connected with Grover search, it will give you the values of these 4 qubits that gives the answer 1. So in Grover search, whatever function you implement as phase oracle, in Grover search, whatever function you implement in phase oracle, it will highlight those values of the inputs that gives the output 1. So Grover search of the magic of unstructured search is that you make a phase oracle, you superpose the inputs, you say that input can be anything between 0 and 1. And after the diffusion operator, only those inputs are amplified, which gives the output of 1 here, or in other words, which gives a phase flip at the ancillary qubit. So any problem that requires to search all possible combinations of input for a specific function and find those input combinations that gives the output 1 can be searched through Grover search. Now let it be the shortest, whatever your aim is, you make the phase oracle according to that problem. And first you have to dilute that problem and divide it into AND or XOR and NOT gate, design that circuit, and then implement it. So that's all from my side. Thank you so much. If you have any question, you're more than welcome. My apologies, I really made you work. But any questions, I'm happy to answer. या कुछ समझ नहीं आया या बहुत समझ आ गया. Okay जी, I think over to Dr. साहब. मैंने टाइम से पहले अगर आप कहते हैं तो मैं प्रैक्टिस एग्जांपल्स दे देती हूँ, अदरवाइज आई डन. हेलो नो सर देख ले कोई ऑनलाइन क्वेश्चंस हैं तो हम उनको आंसर कर लें.
There must be many questions here.
So the practice questions are there, and the circuits are also there, and the phase flips are also there. So for your practice, you can always use those. Okay. Okay.
I read all.
Oh, we have got the answers, circuits as well. So, Eamon Eamon, you're absolutely right. Thank you so much for the circuit. Thank you so much, Fatima. थोड़ा सा ऊपर जाएं. Eamon is giving me the answer. Thank you so much, Eamon. Do we need to add something here or draw something altogether new? Fatima, you had to make a new circuit, and Eamon has answered the circuit in the chat. So we have that answer. Okay, go up. Fatima, for what purpose? What is being asked here? One extra qubit is required. Okay, again, still we were solving this question, Fatima, and Eamon has solved this question and given in the chat, so you can see. The question was Q0 and Q1, bracket close, XOR Q2, XOR Q3. I'm sorry, I don't have access to board, otherwise I would have written it. Thank you so much. Okay, so I think it happens, but at Alice end, time to measure Q states are destroyed, so the meaningless info on classical channel if it's eavesdrop. I mean, less information is not the right word. No information is the right word because we cannot eavesdrop it because of no cloning theorem. Okay, next up. In teleportation, are we using classical communication channel? Does eavesdrop happen or not? Okay, in teleportation, we use classical channel for communication, but eavesdropping is not a possibility because it does not give you any useful information because you'll get 0, 0, 0, 1, 1, 0, and 1, 1 in equal probability. So once you eavesdrop an information, the answer would be 0, 0. No matter what the value of qubit is, you'll get all possible classical values with the same probability. From a particle with Alice to another particle with Bob. Yes. Okay, ऊपर जाएं. We don't share a real particle, can't share matter, we can only share the state. Yes, that's why I was really hesitant saying that we can transfer matter. Thank you so much, Fatma, for backing me up. 25%, 25%. Yes, Fatma is very active and Eamon is very active. Thank you so much. Okay. Okay, Ji. Thank you so much. Okay, the last thing that was left is Varda would be announcing the winner for our last quizzes. I'm sorry, I had to bring a chocolate, but I forgot. So I'll just announce the winner. Javeria Batul. Do we have Javeria Batul in our... Oh, congratulations, Javeria. So she answered 8 out of 9 of our quiz questions. So a round of applause for Miss Javeria because she solved most of the questions. Thank you so much. Anything else? No chat questions? Nothing else? Nisha chali jaye. Okay, I think we don't have any questions. For the next session, 210, it was 230. Thank you so much, Subhansa. Rare winter with shared participants and certificates, please. So training material, I don't know if it will be shared or not. Okay.